Yeah. So again, let's get started. If you can share the slides, that would be fantastic. And we'll get going. The topic obviously is cloud computing and carbon emissions. To start a little bit broader, a lot of what people are talking about these days is sustainability for a number of obvious reasons, I hope. And in IT, we like our boxes, our categories, our classifications. And what I've seen quite a bit is that people differentiate between, on one hand, sustainability by IT, and then on the other hand, sustainability of IT. By IT basically means we're using IT solutions to improve the sustainability of something that is not directly related to IT. It could be the optimization of a logistics company that they drive shorter routes and therefore are responsible for less carbon emissions. All of this is super exciting and a topic of a lot of debate. I don't want to talk about that today, though. I will really focus on sustainability of IT. So these are the carbon emissions in particular of the IT solutions that we, and I say we in a broad sense, people in the IT industry, that we are responsible for, or the solutions that we're actually building. I've structured this presentation into 3 parts, and I'll rebalance it a little bit, knowing that you had a couple of speakers in this series of webinars who also talked about similar concepts. So I will still go over some of the basic concepts for those of you who are not familiar with them, but I'll definitely keep them briefer and then spend more time in the later section of this presentation. As I said, a number of core topics are essential, and one of them is carbon efficiency. Very quickly, oftentimes, and you will see that throughout this presentation as well, people talk about CO2e. The E here is not representative of the word emissions, but just equivalent. The idea really is that we have multiple different greenhouse gases. CO2 is the most prominent one, but there are others. And what is basically happening is that we want to look at all the greenhouse gases and are therefore finding ways to normalize and to convert, if you will, in the estimation, the other greenhouse gases to CO2. So the E is for equivalent, but we look at CO2 emissions, and in English, we often just say carbon. The first really important concept, and I do know that some of you are familiar with it from other presentations, is the idea of energy proportionality. And the idea really here is that there is some correlation between how much workload there is on a computing device, a server in most of the cases that I'm talking about today, and the actual power consumption. The data, and I've really tried my best today to give you only data that is sourced properly, and normally when there's some diagram like this in the top and the bottom left corner, you should see enough information to actually find the report. Because there is not that many reports available, but there's a lot of data that is data that is being cited, and you don't really know where it came from and what the context was, and the context often, of course, is very important. So here, a report from Microsoft in which they looked at, I think it was about 20 reasonably used servers. And what they found in that one is that if you look at the actual consumption, there is this correlation that we would intuitively think about. And what we can see, though, is the line doesn't cut the y-axis at 0. That means, of course, a server that doesn't do anything still uses energy. In this case, about 25%. That is actually much better than it used to be, mostly due to advances in the CPUs that were driven from mobile phones, for example, because they also needed to be much more energy efficient when they weren't doing anything for the battery to last longer. What is really important from this one here, it's a little bit of a mathematical trick, but many servers that we find, especially in on-premises data centers, are not utilized a lot. And that means, in this example here, if you go from 10% utilization, that it uses 10% of the CPU power available, up to 40%, the energy only increases by a factor of 1.7. So in the end, you can do 4 times as many calculations, but you're only using less than 2 times as much electricity. As I said, it's a bit of a trick. If you do this further right on the curve, the numbers don't look quite as nice. I mean, you still get something cheaper in the end because the y-axis isn't cut at 0, but it is still a good idea, I guess, from this one you can see, not to have servers sitting around idle, to design and architect solutions so that the servers are utilized as much as possible. That's also reasonable from another perspective that I'll come to in a minute. What is also important, though, as a concept is the so-called power usage effectiveness. And this is accounting for all the electricity that is being used in a data center that isn't consumed by the servers directly, but by auxiliary systems like light, AC, UPS, and so on. And it is calculated in the way I'm showing on the slide here. If, for example, you're using 10 kilowatts of power for the servers and 2 kilowatts for the auxiliary systems, the total input of the data center is, of course, 12 kilowatts. And that means the factor is 1.2. You're using 1.2 times as much energy as the whole data center than you would for the servers alone. That's actually a pretty decent factor. I'll come back to that later in this conversation. So now, why is it also a good idea to have the servers utilized a lot? The servers aren't only responsible for carbon emissions when they're operating through the electricity they're consuming, but also the production of the servers. The data is even harder to come by. There's this report that I'm showing here that is quite extensive, 70 pages long, and it covers a pretty standard Dell server. If you now think you can get this for other servers, that's not the case. It's very, as I said, very rare, but sometimes you get the detailed information. And here, the summary of 70 pages is basically 50-50. 50% of the carbon emissions are caused through the production of the server and 50% at use. And then on the right-hand side, you can see you're getting a little bit back, actually, due to the recycling at the end of life. Now, of course, there's a huge amount of assumptions being made. Assumptions like how long is the server being operated? How much load is actually on the server as in compute load all the time? And that would change, of course, the height of these columns dramatically in relation to each other. So what I guess you can gain from this diagram is to say, if we can operate the same servers for longer, if we don't write them off after 3 years, but say after 5 years, then in relation, the manufacturing emissions will be less than the use emissions, which is a good thing. Similarly, if I can load the server up with more workload, with more CPU utilization, again, this would change because then would use more electricity and still the manufacturing cost would be fixed. So using the servers more and using them for a longer time span diminishes the impact of the production emissions, the so-called embodied emissions. Another important concept, of course, is that of the programming language. Again, there's not that many reports, but here's one that was published by a team, Brazilian Portuguese team in 2017, and they ran a number of standard industry benchmarks. Not industry benchmarks as in database benchmarks, but more like benchmarks that you would use in computer science, to be honest with you. And they implemented those benchmarks idiomatically in a number of different programming languages. The list is actually longer than what I'm showing on the slide here, much longer. And then measured energy, time, and memory usage. I left off the memory usage. It is not interesting to us here. What we can see quite clearly is that they are very different in the time and energy consumption. And if you haven't spotted it, this is actually a logarithmic chart. So you can see the y-axis is being logarithmic. That means in absolute terms, of course, they're even further apart. But then, of course, the two tall ones on the right-hand side would make everything else look exactly the same. What I find interesting from this chart are two observations. One is that the intuitive notion that if a program takes longer, it uses more energy is corroborated by this diagram. You can see that on the whole, the height of the columns, the orange one, which shows you the energy usage, and the blue one, which shows you the time, that they are very similar in most of the cases. There are some exceptions, and there's explanations for those, I guess. But on the whole, we can say something that takes longer to run, uses proportionally as much energy. The other one that is interesting, of course, is the scale of the difference between the different programming languages. The study here is designed so that C is the basis and everything else is expressed as a factor of the C programming language. And we can see something modern like Rust is very, very close to it. What I personally found interesting in two ways is Java. Java is not a fully compiled language. It uses a runtime, and it's still, I think, very respectable from the efficiency. Like it's only, and I really mean it honestly, it's only twice as bad as C. And if we think about having to implement, say, a set of microservices in C, I think it is relatively clear that Java still would be a better choice. But we can also see that despite all the advances that have been made in the JavaScript runtimes, the JavaScript version is really just not as competitive. And there's maybe a point where you could ask, is it worthwhile to just use a different programming language, given all sorts of other consideration, obviously, and maybe implement this in, say, Java or C# and get immediately a reduction by a factor of, I guess, roughly 2. Last observation, in case you noticed, I mean, Python is the language on the far right. It has terrible, terrible energy efficiency in this study, and I guess in general. A lot of people might, I've gotten people ask me this question after having done this presentation before, and they said, isn't this terrible for all the machine learning that is done in Python? And I would say, not really. Python is used as a glue language there, and all the heavy lifting, the actual computations, are not implemented in Python, but in C or in actual hardware. Next important concept is carbon awareness. And here we're looking at a very different unit. We're looking at grams of CO2 equivalent emissions per kilowatt hour of electricity. So we want to say how much CO2 emissions are caused per energy that we are using. And here I have a chart. This is a few months old. The chart exists, the data exists for other regions and current time as well, but it doesn't really change in substance. We see here the energy mix of the Germany electricity grid over 1 week. And you can see, handily done in yellow, this is the energy that is created by solar power, and green by wind. And we can see it's a weekly chart. There are 7 of these yellow peaks. That is when the sun comes up during the day. And of course, there is no solar power in the night. What we can see, though, is that it changes dramatically. And if I run a workload at, say, point A in time, the electricity mix in the electricity grid is much more carbon friendly, much more sustainable, because I get so much more wind and solar energy. Whereas if I run the same workload only a couple of hours later, when the sun has gone down and the fossil fuel power stations are ramping up, then of course the carbon mix wouldn't be as good. Of course, the previous chart was just stacked to 100%. The reality is slightly different, and this is the chart that doesn't pin it at 100%. We use more as a country, as a society, we use more electricity during the day than at night, and you can see this in the black line in the diagram here, and you can see how that black line, of course, is hugging roughly the production of the electricity. You can't store electricity in a grid. You can see, though, at those points that I picked on the previous chart, that there's actually more production than consumption within, again, this is the data for Germany, within the country. And then you can see at the bottom of the chart into the negative, this is then electricity exports to another country. Here you could argue that you almost get the electricity for free. If you only look at the system from a single country's perspective, there's more energy produced than is actually used, which means you can run the wind turbines a little bit more, which would mean that if you are running compute at that time, you're using electricity that would otherwise go wasted, or again, as I said, on a European level, of course, is then distributed between the different countries, but you could make the same case, I don't have the data, on a European level. Similarly, like time, you could shift the electricity, so the workload, and you can look at the electricity consumption at a regional level. And we can see that the production and consumption is not the same thing in this chart. I've chosen consumption because it matters more for our use case. We want to see how much does the grid actually provide to the cloud providers. And I've picked as an example here Finland, and you can see that it would be 40 grams of CO2 emissions per kilowatt hour. I've picked Finland for a particular reason, to show the difference between renewable and low carbon. You can see the data actually shows 96% low carbon, but only roughly 50% renewable. The reason here is quite simple. Finland uses a lot of nuclear energy, which is low carbon, but not renewable. And you can see a similar thing happening in this chart very quickly with France, that is also relatively green. It has been pointed out to me that this one in particular does not take into consideration the CO2 emissions that result from the construction of the power stations, which apparently with nuclear power is a factor, but I don't know this for sure. To give you an understanding of the size of this, here is the card on Hugging Faces. Hugging Faces is a website where a lot of machine learning models are being shared by the creators of the model. And the people who did Stable Diffusion, which is an open source image generation system, where you can enter a text prompt and the system outputs an image that matches the text prompt. And you can see that they said they used 150,000 hours of these NVIDIA GPUs, the A100 GPUs with 40 gigabytes of RAM. And they did this at AWS, the cloud provider in the US East region. And in the end, they say this produced or was responsible for the production of 11 tons of CO2. So now you can think for certain areas, it should already be relatively obvious. If we could shift this to, say, a different region, we may reduce the CO2 output just without doing anything other than shifting it to a region. We don't have to make a more optimized algorithm. We don't have to change anything. We can just go where there is greener electricity, or we shift it by time. This is actually, I would call them experiments, but this is being done at the moment already for, say, iPhones that are charged in California. They are charged at a time when the electricity mix in the grid is better. And as far as I know, Microsoft is also experimenting with updating the Xbox consoles also at times when the electricity mix is more favorable. As a summary of this bit here, we can think about green software from two different angles. On the one, we can look at carbon efficiency, to use the hardware better, to make the software more efficient, or on the carbon awareness, where we don't look at that, but we look at what does it mean when we run our software and where do we run it for the carbon 2 emissions. Now, second section of 3, measuring and estimating emissions. And I will be very honest with you, almost all of this will be about estimation. There's one slide at the end that actually talks about measuring, but that is, as far as I can tell, the state of where we are at the moment. Here's a website that I guess some of you know, Etsy. It's a marketplace for handmade goods. Etsy has been a client of Thoughtworks. I don't know whether you know this. Thoughtworks is a consulting company. We help lots of other companies writing software and developing custom solutions. So we used to work, or we are still working with Etsy. And we also worked with them at a time when they were thinking about moving from their own data center, from an on-premises or rented data center, to a public cloud. But what they had already said beforehand, and if you maybe guessing by the screenshot already, or if you know something about the company, they do care to a larger extent maybe than others about the environment. And they had already started thinking of saying, we want to actually make sure that we use less electricity for the cloud solutions that we use. They were realistic though, and of course said, of course, if our customer base doubles, if we have twice as many customers, it would be okay if we have a bit more electricity use. It would still be, and this is the middle chart, if the electricity use roughly tracks the business development, as in the number of people, the number of operations we do on our websites, that's probably okay. That's the middle one. We would like to be on the right-hand side where we can say, maybe have twice as many customers, but only 1.5 times as much electricity use. Where we definitely do not want to be is where the electricity use rises more steeply than the actual business development. So this is what they wanted to do. They had only measured the electricity output. And they said that's actually probably fair enough. As you will see later, there's a strong correlation, of course, between the electricity use and the CO2 emissions. So they said, for our purposes, we only measure the electricity output and try to reduce that. Sorry, electricity input that we need. And this is what they did. You can see the chart here in 2016. They knew how many kilowatt hours they were using. This is all from a blog post that was linked on the previous slide that they have published. And you can see how much electricity they used. Then, of course, they started moving to the Google Cloud and couldn't get the electricity usage anymore. In your own data center, you know how much electricity you're using. If you go to the cloud, it's not only that the cloud providers don't provide this information. I don't think they could actually honestly provide the information because the cloud infrastructure is, of course, shared in many different ways by different customers. So what Etsy then said is, but we still want to have some feeling of how much electricity is being consumed on our behalf. And they came up with this strategy. They called it Cloud Jewels, to actually estimate the kilowatt hours of electricity their cloud solution would use. And I'll go into detail about this on the following slides. On this one, I do want to point out at the bottom, look at the difference in PUE. The PUE in their own data center was 1.4 almost, whereas on the GCP, it was 1.1. That's basically a reduction of 20% of the carbon footprint right there, just by having a different, more efficient data center. Oops. As I mentioned, Etsy was a client of Thoughtworks. We saw the code that they had written. They made the code available on GitHub. Thoughtworks is a company that does like open source. We do like to try new things from an engineering perspective, not only write and speak as I do now, but also with software. And we took what Etsy had and ran with it for a while, and not for a while, like for a bit, and said we can maybe make this a bit more generic, make it work in the different cloud providers, not only on GCP, and created this tool called Cloud Carbon Footprint, which is today still available as open source software and works in GCP, Azure, on AWS, and also in Ali Cloud. And it basically takes the same idea and says, okay, we want to somehow estimate the electricity usage in a cloud solution when we cannot get the true electricity use from the servers. And the methodology that all of the tools, and I mentioned a couple of others, is that they use is very, very similar. So basically you're starting on the left-hand side and you look at the consumption. You look at the consumption, compute, and storage. This is what Etsy used initially. And then there's other components like networking and memory. And I would say Etsy was completely correct in not looking at networking and memory at the beginning. By memory, I mean the RAM in the servers. And because they are actually negligible, they're not as much of a factor as compute and storage. So they started with it, but because we could, we in Cloud Carbon Footprint also added networking and memory. There are different ways to get at the usage data. Sometimes it's the billing API. Azure has a consumption API. There's all sorts of ways of how you can get this. And you can say, I used 1 hour of virtual CPU time on this kind of instance type. That gives you the usage. Now the question becomes, how do I convert the usage into kilowatt hours? How much electricity did I use? You can use some standard factors, and that's indeed what Cloud Carbon Footprint and the other tools are doing as a fallback when more detailed information isn't available. But there is more detailed information available, and one that I want to show you in particular is this one here. It is the spec power database that has somewhere between 800 and 900, I think at the moment, entries of server systems that show in detail the power consumption curve of those systems. And here I've looked up the same server that I showed you before in the report about the CO2 life cycle emissions. And we can see, I guess you can see in the orange section, that server at 100% load uses 432 watts of electricity. So now we can see, of course, from the spec data information here, from the spec power data information, what kind of CPU is being used. And there is a reasonable link between the instance types of the servers at the cloud providers and the physical servers that are used for them. And therefore, you can get actually a little better information than just pure estimates that also exist across entire data centers. What you can also see on the right-hand side, this is the curve of energy proportionality that I showed you earlier in this presentation. It is, though, shown in the spec power database with the X and Y axes flipped. And if you do it, I've done it here, because you can't read the text anymore, but you can now see the proportionality here of how much how much electricity is actually being used here. You can also see that the curve is not linear and that the best area of efficiency is not necessarily 100%. So now, now you have the energy conversion factors. You've converted the usage into kilowatt hours. Now you need to multiply that by the PUE that we discussed before, because it depends on your data center. And then the next thing you need to do is you now need to get from the kilowatt hours to the CO2 emissions, which means you need to have some grid emission factors. You want to get to the CO2 emissions. Here again, you can use data that I showed you earlier, like electricity maps, and make statements or assumptions about the data centers and that the electricity mix they consume correlates to the electricity mix in the region or country that you know about. Ideally, you would get information like this that Google did provide a long time ago, many years ago, about the carbon-free emissions in their specific data centers, in the availability zones. Unfortunately, this is a PDF file, so it was a report that was done. It's not a dashboard. And to my knowledge, please let me know in the comments. I can't see them right now. I'll look at them later. As far as I know, there is no dashboard at the moment for either of the cloud providers that show you relatively real, even if it's just the last quarter information. But what it does show you is how different they are even in Europe. And I've cut that longer list down, and you can see the European data centers here, and you can see a huge difference with Europe North 1, which is in Finland, 91% carbon-free energy versus, say, London with only 57%. So here again, the workload shifting would make a lot of sense if you're calculating larger machine learning models, if you have big batch jobs that are not sensitive to latency, that you move them to a different region where you can. There is, I will of course admit that, there is of course, if you need to transfer a lot of data, there is a carbon footprint associated with the data transfer. You can calculate that to a certain extent. It's very, very difficult to do, but in the end, it is probably negligible. If it's really compute intensive, the shifting of the data should not make much of a difference. Now, that means and I don't know whether you noticed, but you can multiply these things, right? The usage, you multiply it by the conversion factors, you get the kilowatt hours, you multiply by the PUE, you multiply by the emission factors, and you get the carbon 2 emissions, almost. Because what we haven't done here is we haven't looked at the emissions caused by the production of the servers. So in the last step that I'm not showing here, you need to also add to what you've arrived at so far, the estimated production cost of the servers. Here again, you will understand, I guess very obviously, this is a bit of a black art, because what does it really mean? If you have used 20 hours of a server, you would probably just approximate 20 hours over a lifetime, over a lifetime of 3 years, and then take that into account. Is that fair? I don't know. Depends on how much the server is utilized, how long the server is being written off. So there's a lot of educated guesswork needed based on the information that has been published. In the end, what you do get, though, is a chart like this. And what I do want to point out is the most important thing really here on this chart is not so much the precise value on the y-axis, it is the directionality, the direction of the chart. I saw a talk by the CIO of one of the of Europe's largest e-commerce websites, and he talked about a similar topic. And he said, in the end, what they wanted was a baseline to see from how much they could reduce the energy consumption or the carbon emissions, much like Etsy did in the US. We want to have a baseline and then reduce it. If there's a systematic problem with the data or with the estimation process that systematically adds or takes away, say, 10, even 20%, it doesn't matter so much because it doesn't change. It is a constant higher or lower, but it doesn't change the direction. What you also can see, though, on this chart here, this is a screenshot, obviously, from Cloud Carbon Footprint. You can see that the yellow and the blue line, one is showing the electricity use and the other one the estimated carbon emissions. You can see that they are very much, they're closely tracking each other, which is, again, proving the point that Etsy made to say, we can actually look at only the electricity consumption, but you can also see that there are examples further towards the right of the chart where they don't completely track each other, where you got maybe some workload shifting happening and you got more electricity use and still lower carbon emissions. The cloud providers have obviously added similar estimation technology to their solutions. At the bottom, there's one of the Google videos running. I'm showing this one. There was all this thing, remember I talked about Thoughtworks working with Etsy going to the Google Cloud, so there is some connection in here. But the other cloud providers have similar tools. I will highlight, though, that on AWS, as far as I know, again, please correct me in the comments if that has changed. As far as I know, on AWS, the embodied carbon is not counted, which means if you look at the Google report versus the Amazon report of your own workloads and think, oh, why is the Amazon one so much lower? It's not because the data center is more efficient. It is because they do not count the scope 3, the carbon emissions from the production of the servers. On the whole, the PUE is very, very similar between the 3 different major cloud providers, so GCP, Amazon, and Azure. But yeah, as I said, the tools are there. You can use them. Be aware that with those tools, you do not know precisely what methodology is being used. You have to trust the cloud providers. On the other hand, I think it is, especially in that regard, reasonably fair to assume that it's not systematically wrong, that the cloud providers are really trying to do their best and give you the data based on what they have. If you want data that goes across different clouds that is roughly comparable, and if you want to know the methodology in complete detail, then you could use open source software like Cloud Carbon Footprint, because there you can install it wherever you want, and you can of course see precisely to the last detail of how the estimates are being made. Just to give you a different idea, this is a completely different tool that only looks at graphics cards. They have written a scientific peer-reviewed paper on this as well. And I've taken the same data that the Stable Diffusion team made available and plugged it into this calculator. You can see I'm choosing the same NVIDIA GPU. I'm putting in 150,000 hours of GPU time in this region at AWS. And the tool estimates it would be 13 tons, 13.8 tons of CO2 emissions. And if you remember, the team self-reported 11.2 tons. So again, we see the data doesn't match precisely, but again, from a ballpark figure, we are getting to something where this is at least meaningful. And then, I promised, last but not least, there are efforts underway to do actual measurement and not estimations. This tool here is particularly interesting. It's called Kepler, works only in Kubernetes clusters, but what is really cool about it, it uses the hardware that is present in the servers and GPUs to read out the actual power consumption. This is built into all the PCs, into servers, into MacBooks, into mobile phones, the graphics cards, and so on. You can actually ask the hardware via specialized APIs, interfaces, how much electricity are you currently using? And this is what Kepler is doing. It is looking at the actual hardware consumption. But then, of course, if you're running a Kubernetes cluster, I guess most of you know what that is, you have multiple pods potentially on one machine, and you want to make sure that you're attributing the current power consumption to the right pod. And Kepler is quite clever in that regard. It uses a relatively low overhead method. It uses the ePPF, the extended Berkeley packet filter, that is used for all sorts of cool things these days, and uses it to figure out which pod is actually currently active, and thus can do the attribution of saying, oh, the server is currently using 400 watts of electricity. This is the pod that is running, so I can add this, and then at least you get very, very close to actual measurement and quite far away from the estimation we've seen before. This is an early days project, and we also have to remember this really works when you have access to the hardware, which is not necessarily the case in a public cloud, unless you get the bare metal versions of the machines. And it certainly will not help you when you're trying to estimate something like the usage of DynamoDB or Kinesis or any of the other, like the software as not software, the function as a service solutions, etc. But again, just to say, people are also researching in that direction. Okay, last but not least, I do want to talk a little bit about the reduction of the emissions. And what is important here is I only want to talk about eliminations, like the actual elimination of emissions, not offsets. I mean, I can maybe show this to you here. If we go back here, on this one, on the Google one, I framed the one which shows the carbon-free energy usage. But if you look at the right-hand side, all the data centers are reported as zero. That is, of course, impossible because they need to use some electricity, and in any grid there will be some electricity that is not renewable or low carbon. What they're doing, of course, is they're buying certificates, and there's a whole market for it. It's an interesting approach to dealing with it, but that is basically just shifting it around between different industry. What I want to talk about is really that column that says how much electricity are we using and how can we reduce the carbon emissions by actually by using less electricity, less energy, or fewer servers. So, how to start this whole thing? You can think of it, and many people are calling it as GreenOps, as a sibling discipline to FinOps. FinOps is something, I guess, with the audience of this webinar, I don't have to explain it too much, is the discipline of actually trying to optimize the financials of your cloud solutions to actually try to spend less money for the same business value that you're creating with this cloud solution. There is a huge overlap with the carbon reduction because most of the time you're spending less money when you're using fewer resources, and when you're using fewer resources like compute, storage, etc., then you're of course consuming less electricity, which means you're responsible for less carbon emissions. So there's this whole overlap, and a lot of companies, when they're just doing FinOps, they're also doing GreenOps to a certain extent because they're reducing their carbon footprint. That's actually counterintuitive to many people because it's ingrained in many of us, I guess, to say that if you want to do something good, it's a trade-off. It will cost you. But here it's almost the opposite. You're doing something good and it's also cheaper. That's not always the case. You can get quite far with just cost optimization, but sometimes you just really have to optimize for energy and emission. You just have to optimize for energy and emissions. And that is, for example, the workload shifting that I talked about. If you move the workload, say, from London to Finland, to stay with the example from earlier, you would significantly reduce your carbon emissions, but that is not something that is going to be necessarily cheaper. It may actually be more expensive depending on how the data centers are being priced relative to each other. So there are certain areas where doing something green is actually more expensive, but surprisingly often there's this overlap and you get something that is good for the environment for less money. In any of this, though, you do need some metrics and some reporting. As I said, I'm not aware, correct me if I'm wrong, there's no real precise measurements, no precise data, so be aware of what the data is like that you have, how it was generated, in which direction you can trust it and what you can do with it. But without any form of metrics and reporting, it is going to be almost impossible to show any benefit of the measures that you're taking. To that extent, I'm not sure whether you know this, Thoughtworks publishes a technology radar twice a year. We put 100 entries on there that we discovered or that we have something new to say for the previous 6 months. And from one of the recent reports, we added this item here. Carbon efficiency as an architectural characteristics. That's a good way to start. For development teams, of course, we're already looking at cloud cost, we're looking at performance, we're looking at security, accessibility, and all sorts of other architectural characteristics. And we are saying in today's age, it is worthwhile to add another architectural characteristic, and that is carbon efficiency, and at least to think about it. As I said earlier, if we know that, for example, the C programming language is more efficient than Java, fair enough. But that is just, we look at it, it's a characteristic, and then still decide, for many other reasons, it would be not a great idea to program this microservice in C. Let's keep doing it in Java, but we have considered it. We made a considered choice. We didn't just stumble into something without thinking about it. One thing that is, I guess, generally true is that using a public cloud on the whole, in general, you hear all the qualifiers, helps with reducing carbon emissions. And there's 3 main reasons for that. One is the data center efficiency. The data centers that are operated by the cloud providers are really very efficient, and there's few other data centers that can get even close to that. Because if you think about the example from Etsy, and this is actually a few years ago, and maybe it's not a perfect example, but the PUE went from 1.4 to 1.1. That was a 20% reduction for Etsy. But the point is, the data center was basically 4 times as efficient. In the Google case, for 1 kilowatt, they only needed 100 watts extra to operate it. In the data center that Etsy was in before, they needed 400 watts, so 4 times as much. And then to think that many data center providers can actually get to that level of sophistication and efficiency as the hyperscalers can get to, I think that's a bit of a stretch. And it is, from the data that I'm aware of, actually borne out in reality too, that the cloud providers have every incentive to be as efficient as possible, obviously, because they sell you compute time. So anything they spent on air conditioning is actually wasted from a monetary perspective. So they're trying to reduce this, and they have the scale to actually do this very well. So the data center efficiency is one reason why going to a public cloud can help you. Another one is elastic resources. You can reduce the amount of servers you're needing, and they're not sitting around idling. If you give a server away, you can be reasonably sure, I would say, that somebody else is picking up the server. I mean, AWS obviously does it with spot instances. It creates even incentives for people to schedule their workload in times when the servers are not needed. But classic example, if you're an e-commerce company, you have to have enough, and you're running it yourself on premise, you have to have enough servers to survive the Cyber Week in autumn, in the fall. But that means that most of your servers will probably be idling for the rest of the year. You could probably turn them off, but you would still then have caused the energy emissions, the carbon emissions from the production of the servers. With the cloud providers again have every incentive commercially to pack the workloads as much as they can, therefore using the servers as much as they can, and they can, to save money, also run the servers for longer. So again, you do, to a certain extent, get that, what is known as scale to zero. You need to be a little bit careful though. Just returning a Kubernetes pod in a cluster doesn't necessarily mean that you're returning the server to the cloud provider. There are scalers who can do that. So the last one then, of course, but I've talked about it quite some time, is the workload shifting. If you have your own infrastructure or if you're running in other data centers, it is not as trivially easy to shift a workload around. If you have your own hardware, I would argue it's relatively impossible to say we want to shift the workload. You could only make maybe a principled decision and say, if you're really heavy into calculating machine learning models, to say, okay, we just rent the servers or we buy the servers and the graphics hardware in a data center in Sweden, in Finland, and we're not doing this in Frankfurt or London. So, but now, independent of cloud or not, maybe to a certain extent, some strategies to reduce emissions. The first example I want to give you is, these are all examples. There's so much more you can do, but I really wanted to make it tangible, concrete for you. The first one is resource scheduling. That's super, super simple. Sometimes you don't have to have any clever algorithms, you just know. And an example that I can relate from past experience was continuous delivery pipelines. You want to have a lot of build agents so that when a team of developers checks in code, the pipeline can run quickly and the team gets feedback quickly whether the changes they made broke the build or not. The thing though is, I hope anyway in most organizations, that people are not encouraged to do overtime, which means if you say, some people start earlier, some a little bit later, but let's say you're in the same geography, you probably need only 10 hours on the working days of the build agents to be present, to do anything, which means you need them for 50 hours, 5 days times 10 hours a day. A week obviously has 168 hours. So if you were to run the servers, you would have a 70% reduction of server needs for the developer infrastructure if you just said every morning at 8 o'clock we start the servers and at 6 o'clock we shut them down. You know what I mean? Sometimes you don't have to do really clever AI or algorithms even. You can just do it on a basic cron job, if you will. But also sometimes it is worthwhile looking at the unexpected. And here's something that I wasn't aware of at all. But if you look at Hadoop, which is a commonly used tool for many data solutions, these nodes do compute and storage at the same time. But compute and storage don't always scale in the same way in any solution. That can mean in a Hadoop cluster where you have storage and compute on the nodes together, you might need new nodes because you're exceeding the storage capacity, but you're nowhere near the CPU capacity. So one thing you could do there is you can configure Hadoop or the solution you have in such a way that you can scale storage independently from the CPU utilization, which means you could then say, okay, the servers are not utilized from CPU power, let's keep that number, but the storage is running out, so maybe we need a couple more servers for storage. So then to sometimes also think about beyond of what we assume and say, are there independent axes of scalability that we can actually tease out in the software architecture? Another interesting topic is batch jobs. In many industries, financial services in particular, runs large batch jobs that do all sorts of calculations. It's not all straight through processing, especially not in retail banking, but also I know many other industries where there's large batch jobs. And oftentimes they run and everybody's just happy that they run, and because they're hard to debug, people don't want to touch them, and then it's like, oh, it might be better to run the job if we don't quite know. But there's a lot of energy and compute resource. This is where FinOps can work as well. Compute resource wasted for batch jobs that run unnecessarily. Sometimes the input data doesn't change and the job is run anyway. Or sometimes data is maybe consumed once a day. The people who produce the data don't know this and run the batch job once an hour. So there's lots of little things you can do. There's also some sensible caching. You can also see what is the data we need and start looking at from the consumption and then see what batch jobs you need to run at what point to actually make sure that the data needed by the consuming side is actually as current as they need, but not more current, which means you don't waste additional energy. What I found super cool though was there's a case study. We have nothing to do with this. This is done between Microsoft and UBS. And they looked at the batch jobs they're running at UBS. And they went further. They went into the direction that I talked about before, this idea of time and space shifting. They particularly looked at the time shifting, which I guess makes sense when you look at the batch jobs. And here's what they have done. I'm trying to explain the diagram. You can see that there's 5 days, and with the red bar, what they're showing is this is based on the estimated energy after the fact the batch job would have needed to run. So that's the red bar. If they just run the batch job whenever they normally would have scheduled it, and then they look afterwards what was the electricity mix in the network, what was the electricity usage in the data center, this is how much CO2 emissions would have been. In gray, they're looking at a forecast. You can ask electricity maps, show me what the electricity mix is likely going to be in the next few hours. And then you can say, okay, this batch job has a window. It doesn't have to run at midnight. It can run at 2 a.m. in the morning as well. If at 2 a.m. the electricity mix is better, I'm going to shift it by 2 hours. Of course, you're relying on a forecast. And that is what they're showing with the gray line here. And they're saying, this is what the algorithm said, if we run at the optimal time, this is how much CO2 emissions we would cause. And then in yellow, they're going after the fact and say, now we ran it at the optimal predicted time. What did it really mean? Because the prediction, of course, is not 100% accurate. And that's the gray, the yellow one. I guess what you can see from this chart is that without fail, both the gray and the yellow one are below the red one. In 1 or 2 cases, I think they're very close. You probably can't really make a statement. But on the whole, it was definitely not a mistake, I can say, from this one to do it. And even though sometimes in the second day on September 20th here, you can see that the actually used was not as good as the prediction did say, but on the 19th, it was the other way around. But actually shifting this around, this case study, it's actually a reasonably detailed PDF document you can look at. You can actually get a feeling for that it does actually make sense to spend some time and development energy into improving batch jobs, for example. And then last point for today, machine learning. I talked about this quite a bit. A lot of people are talking about it. I guess we're a little bit over the hype curve and fewer people are really considering to train their own large language models, but there is still a lot of ML training that is happening, fine-tuning models, calculating embedding models, and so on. So there is still a lot of that needs to be done. And when there's a lot of CPU time needed, of course, we can think about shifting the workload by time, by the geography, but there are other techniques as well. And here, I've just shamelessly copied a slide from a Google presentation that shows you a number of different techniques that are recommended in there. I was in a debate with myself what to do, because I mean, all of those you can almost do a half-hour talk about each of those points. So I can't really go into detail, but I just wanted to show you that there's a whole spectrum of things you can do. You can look at something like tf-hub.dev and see, is there a model? Maybe I don't have to train my own model. That is a lot of CO2 emissions saved. But there's also things that maybe you haven't even considered, like exploring the hyperparameter space. That's very, very important in machine learning to get the hyperparameters right, and you won't get them right. And it's a bit of a black art, to be honest, if you're not familiar with it, to get the right hyperparameters. So people try all sorts of things to get the right set of parameters. But then there are tools like Vizier, in this case from Google, that actually help you to do this more systematic, which means you have to run the model generation fewer times, which again reduces carbon emissions, and so on. Last thing to also mention them, because I think that was a great effort, AWS has this well-architected framework if you are on AWS, but even if you're not, it's actually worthwhile looking at. And they've extended the well-architected framework with some recommendations around sustainability. I'm just showing you some of them here so you get a feeling for it. This is also for experienced practitioners. It is something worthwhile looking at, it almost like a checklist. You can just go through it and say, hey, did I cover this? Is this something that we might be able to do? Have we forgotten about this? Or at least it gives you the assurance in saying, okay, we've thought about all those things. We have, given the other trade-offs we have to make, we have found a great solution for that. The list is, and of course, you're not expected to be able to read this, just to give you a feeling for, this is the entirety of the list. So I think it's a good level. It's not daunting to the point where like, okay, we have no time to actually look at this. This is too long a list. We can't go into detail. But at the same time, it's not so short as to be trivial. Where you're like, yeah, okay, everybody knows this. We don't need to do it. Okay, that's what I had. Thank you for listening and staying around, I hope. And now I'm happy to hear questions, answer some questions.
Thank you so much for this talk, Erik. I think we have some comments in the comments tab. The first one says, how can organizations effectively educate their users about their environmental impact on their cloud usage?
Yeah, depending on when the question was asked. I mean, this is, I guess, what I showed with the footprint tools. I mean, that is the best way of doing it. I mean, I don't know, it's always hard to generalize, right? But I mean, I work as a consultant. The companies I see, they often already have dashboards where they can see the cloud cost. They often tag the cloud resources by business case. So, you know, I mean, like they don't tag them by this is all database, this is all web server. They tag them by saying this is for, say, order capture, or this is for article display, and so on. And then, of course, you can do dashboards that show you how much you're spending on the individual business features. Also shows you of how many resources you probably can delete at this stage. And at the same time, with a tool like Cloud Carbon Footprint, or the ones that the cloud providers have, you can then, if the resources are tagged correctly, the individual business units can see how much CO2 emissions they're responsible for.
All right. So the second one is asking, are you seeing an increased adoption of green cloud services by businesses? And how significant is the impact of these services on promoting sustainability within the IT industry?
Yeah, it's a tough question because the green is in quotes, so I'm not quite sure what that means. I mean, we definitely do see more and more organizations go to public clouds, if that's what you meant, that the cloud services are green, and with some caveat, that's, I assume, what you mean. There's fewer and fewer organizations that run IT solutions on their own premises. And then there's, of course, this middle ground where it's not a hyperscaler public cloud, but where you just own, like, say, 10, 15 racks in some data center. We're seeing a general shift from those into the public cloud. And then, as I said, you will always, I'm sure there are cases where you can show me an example of a perfect data center, somebody who did really go out of their way, who are just building something on top of some hydropower, you know what I mean? But on the whole, the cloud providers do work there, and the trend is definitely there.
All right. So I think the third question is already answered. That have you seen any successful examples of implementing usage policies to encourage responsible resource consumption? You already mentioned it during the first answer. Do you have another one? Can you discuss the importance of sustainability certifications in the cloud industry?
Yeah, we have a few minutes. It's as good as in any other industry in the end. I mean, this is the idea that you can trade CO2 emissions. If you have CO2 emissions, you can pay somebody else money who bought the certificate for something. So they can somehow demonstrate that they are reducing or not using things, let's put it that way, that produce CO2 emissions, and therefore they can provide the certificate and you can buy it. So you can trade CO2 for money. In the short term, this is actually not necessarily, this is my personal opinion now, it's not necessarily a bad thing, because at least on a system level in the entire industry, it puts a value on CO2 and it encourages the system as a whole to reduce the CO2 output. It has a downside though, because it can encourage behavior where companies, especially cloud providers who do make a bit of money, where they could say, we just buy our way out of it. Why should we ever optimize for CO2 emissions? We just price it in. 1% of the revenue we make, we pay certificates, and then we say green cloud, and we're done with it. So it works both ways. I think it's a good intermediate step, but that's why I said in the last third of the presentation, I really want to focus on techniques that are not to do with certificates, but really with reducing the actual resource consumption.
All right, and we have 2 more questions. When considering efficiency in the continuous integration process, how does the practice of building and testing artifacts for every commit in a continuous integration service with green software contribute to overall workflow efficiency?
Yeah, that's a great question because, of course, even Cloud Carbon Footprint itself has a carbon footprint. It really depends on the solution you're building. If you're building a massive e-commerce website, the resources used by the software development process itself are completely negligible. They're like a fraction of a percent. If, on the other hand, you're writing a software system that is used by very few people and is only maybe used once or twice to calculate something specifically, then of course the CO2 emissions caused by the production of the software itself, they can become significant. I wouldn't go as far as saying that we should look at reducing the number of unit tests or automated acceptance tests, because they also of course use electricity for the sake of reducing the carbon footprint. But as I said, I'm sure there are some extreme cases where this could make sense. On the whole, though, again, there are other parallel incentives. A team generally wants fast feedback. So a team should, in general, try to make the build as fast as possible, which means they're trying, coming back to the earlier slide about the programming efficiency, if the build is faster, if it takes only 20 minutes and not an hour, they're also using less electricity. So there's an incentive for the team to actually run it more quickly and therefore have less of an impact.
All right. And we have the last question. What do you think is generally the lowest hanging fruit for businesses looking to reduce carbon emissions, if you had to choose just one?
Yeah, I think I said it already. The most obvious one is public cloud. That will probably give you the biggest gain for the least amount of effort, depending on how you're set up before. But on the other hand, you need to be able to see what you're doing. You need to be at least at the stage where you have some visibility of the resources that you're using.
All right, so I think that's a wrap. We are almost 1 hour. So thank you so much for this talk, Erik. We're looking forward to implement these valuable insights in our practices, and we will have a look at the Thoughtworks technology radar for sure. Thanks very much again for your talk. We hope to see you again, and let's keep in touch and have a good day.
Thank you, Ivan. Thank you for having me.
Goodbye.
Bye-bye.